And it's all about arrays. And here you can see that the first argument is declared as an array of int. An array is a sequence of values, all of the same type. So this is a sequence of integers. You could have an array of double, or an array of string, or an array of anything, any other data type. So this is an array of int. And so you have a sequence of values. Now the information about how many values are in the sequence is passed in separately to this function here. So we're showing a function as the second argument. So here we have a second argument, which is an int called number of elements. That's how many elements are in the array A. And the problem here is to find the maximum value in A. So what is the largest integer in A? And return that from the function. So the return type is int. So this is one of the problems you need to do. Here's another problem. Count occurrences. This is a function, count occurrences. It takes as its first argument the array A. So the name of the array will be A. And that's arbitrary. You can pick any name you like. It's an array of integers. That's why it starts with int, int A, and then the bracket there, that means array. Then the second argument is information about how many items are in the array, the length of the array, or len. That's just a commonly used variable name to represent length, but it's not always used, just sometimes you see it. Then the third argument is an integer k, and the problem is to count how many times k appears in A. So A is a sequence of integers, and k is a specific integer. Let's suppose that A is 3, 3, 7, and 11. 4 integers, 3, 3, 7, and 11. And if k, and the length is b4, so the second argument gets a 4. If k were 3, then the function would return 2, because there's 2 3's in that sequence, 3, 3, 7, and 11. And if k were 100, the function would return 0. There's no occurrences of 100 in A. That's that one. Now, arrays can, in addition to being single dimensional, they can be two-dimensional or three-dimensional and so on. So you look at this, this is a table. You can visualize this as a table of 50 rows and 100 columns. Here, this array here is, there's no information about its size. So we have to pass in the size information separately. But in this case, the size is declared in the argument right there. So we don't need to pass the size in as a separate piece of information. And there's two sizes. There's the number of rows and the number of columns. So you can think of a spreadsheet with 50 rows and 100 columns. And the problem here is to implement this function is all zeros. So is every element in A a 0? True or false? If every value in A, if every integer in A equals a 0, then we return true. It's all zeros. If there's at least one non-zero element in A, then we return false. So that's that problem. Let's look at this one. Are identical. Here, we pass in two arrays, A and B, and the function returns true or false to indicate whether the items in A and B are pairwise equivalent. So if A were 3, 3, 7, and 11, and B were 3, 3, 7, and 11, the function would return true. A and B are the same thing. They contain the same values. But if A were 3, 3, 7, and 11, and B were 9, 9, 0, 0, then the function would return false. They are not identical. And of course, the third argument is the number of elements in the array, both arrays. They won't, if they have different sizes, they won't be equivalent. So we just assume that they have one length. Here's another problem. By the way, these are all very easy problems to solve. You'll see. There's not much code involved. Is unlucky. This function returns true or false. If A is a lucky array, it returns true. And if A is an unlucky array, it returns false. Oh, sorry, it's the other way around. If A is unlucky, right, it returns true. If it's lucky, it returns false. Is this an unlucky array? And, you know, this is just make-believe here, right? So if 13 appears in the array, then it's unlucky. We just say that. That's our definition of an unlucky array. And then we have this function. This is the hardest one to solve in this set of problems. Is strictly increasing. Is A, are the elements in A, are the values, the integers in A, are they in strictly increasing order? Return true if they are. If they're not, return false. Here's an example. These values, these integers, are in strictly increasing order. These values are not. They're increasing. They're non-decreasing. Yeah, they're non-decreasing, we'll say that. But there's 2 6s in there. So that's what the word strictly is ruling out. So strictly increasing means it always goes up. It doesn't flatten out. It certainly doesn't go down either. So is A strictly increasing? And you can imagine the variations. Is it strictly decreasing? Is it non-increasing? Is it non-decreasing? All those variations we can define and solve those problems. So this one is, and these are, here's the arrays. So let's talk about arrays now, more with an example rather. With an example. I'm going to print all tests passed. So I'm just going to get warmed up here. Make sure that I've got a good shell of a program to get started with. Looks good. Now these problems, they all ask for you to write test code that thoroughly tests the function. The test code should use assertions. There it is. All of these should be tested. And use assertions. I'm going to show that to you. I don't know, did I show that yet? How to use assertions for test code? Did I show that? No. So it's all the same thing. So the method of testing is uniform in this set of exercises here. So we'll have some kind of a function, like let's pick one out. Is we'll do this. We'll compute the total. So we'll write a function called total. It'll take an array of integers. It will be of size n. Maybe n is, I like small numbers, but let's just call it size, all right? The size, or maybe we'll call it length, all right? So we could n, size, length, you know, we decide what we want to do there. Yeah.
Today's Thursday, right? Tuesday was the first time you used a non-predefined function. The first time you wrote a function in front of us.
Okay.
So I just wanted to make sure I knew how to write a function. You just define the output you want for it.
That's right. That's here. That's the data type of the output. The data type of the output.
So the data type of the output, the name, and then
the name of the function. Yeah, I'm going to slow you up there. Okay.
sorry.
Data type of the output, and then the name of the function, and then what comes next?
The input, the data type of the input.
Exactly, the data types of the inputs, because you can have 0 inputs. You know, 1 input. You can have 40 inputs. So you can have any number of inputs, and if you have more than one, they're going to be separated with a comma. And each input is preceded by the data type. So that's a pattern that reoccurs. The data type is used. When you're declaring something, you precede it with the data type. See, main is a function. We've been working inside main. Main is a special function. What is special about main? It doesn't have any input? Well, actually, it does take some input, but we can optionally leave it out. So it takes something like, maybe it's the other one. Maybe that's the second argument. I either got these reversed or it's, let me see if I got that. Main also takes an input, but the compiler lets us omit it. Maybe it comes first. What is it? Arg. Argnum. That's not what's usually chosen. That's not what usually is used. These are the number of arguments. I think it's usually like this. Argc, argv. How do they do it? They do args and argc. Is that how they do it? I don't remember. Anyway, this is the count of arguments on the command line, and this is an array of char pointers. So the array of strings, which are the command line arguments. I don't know. I don't want to get too distracted here. If we print argc, you'll see, we'll investigate with that. This should say 1. I got it. So I had to predict it first. And it's the number of arguments on the command line used to, it's actually not arguments, it's the things on the command line, the symbols on the command line that are used to run the program. So we only have one sort of symbol on the command line that's used to run the program. It's the name of the program itself. But if we ran the program with, say, an argument, like say Fred, now it says 2. And then Fred and Sally, now it's 3. There's 3 items on the command line. So that gives you the number of items on the command line right there. Now this gives us access to those command line elements, like I'll show you here. So this will print dot slash a dot out. See, dot slash a dot out. And if if we print the next one, it'll be the second argument, which is Fred. So we print C, which is 3, because it's 3 items on the command line. And we print args0, which is the first item, that's ./a.out. And args1, which is the third item, Fred. So this is used to access the command line that was used to execute the program. So main is a function. Now, I got off on a tangent, but every quarter I teach this class, this question comes up, and the students always want this explained. So there it is. What else is special about main? I mean, it's obvious, I think. Main is called the entry point. If we didn't have a main function declared, it wouldn't compile, because the compiler doesn't know where execution starts. And it's a linker error, actually. And it's impossible to read that. Look at this right there. Here it is. I can read that part. Undefined reference to main. We didn't define any reference to main, but there's an implied reference. Main is the entry point. There has to be a main. Otherwise, the linker doesn't know where to start execution. LD is the linker. That's the program that takes the compiled object code and wires the whole thing together with connections to the operating system and produces the executable. It's the final step. So it'll compile this, it's compiling this, but it can't execute that final step, which is to wire everything together, because it doesn't know where's, I got the wire to plug into main, but I can't find the main. So it's complaining. So the linker complains. So that's, whenever you see LD like that in your error message, you know that's a linker error. It's not a syntax error. Get rid of this. Now we have a main defined. In the old days, it was required. This is the function. You had to define it like this. There's no variation. But, you know, at some point, compilers were more forgiving, or written in a way that they became more forgiving, and you could omit the arguments. And so this compiler takes that version of main. Anyway, main is a function. We don't call it, the system calls it. And when the system calls it, the system passes in those arguments that I showed you. But we call total. So we're going to call total. When we call total, we're going to pass in an array and its length. And total returns an integer. Let's print it out and look at it. We're going to pass in an array A, which is of length 4. 4 elements in A. And we want the function to add all the elements up. So, and by the way, so the test code will be like this. We want A to be 3, 3, 7, and 11. Now, it doesn't have to be an increasing sequence, so I'm going to show that to you as 3, 3, 11, and 7, just to make sure that we remember that. It's not, the values don't have to be in any particular order for this problem. So the size of A is 4. There's 4 elements there. And there's an element in the first position, which is position 0. And there's then followed by position 1. followed by position 2 and position 3. Those are the position numbers for those values. You can access the value at position 1 like this, as an example. So it will be A of 1. And that prints, what does that print? What does that print? What's that? A of 1, not quite. See, A of 1, that means I want the value in A at position 1. This is the syntax. I want the value in A. Remember, A is a sequence of numbers, or a sequence of some data type. In this case, it's numbers. So A is a sequence of numbers, and I want the number in position 1. Starting, from position 0, we count from 1, 0. Can you revise that guess? 3. That's right. 3 is the value that's in position 1. It's like we numbered the chairs in this room. You're all who you are. But then we can refer to you by chair number now. So we're referring to this 3 by its position in the sequence. It takes a while to get used to this. The main hurdle, conceptually, is to distinguish between the position number and the value at that position. So in code, you're going to see this a lot. See that? A bracket I. This expression evaluates to the value at position I in A. Right? I is the index number. It starts at 0, goes all the way up to the length of the array minus 1. And then this expression says, get me the number, get me the value that's in position I. You have to keep, I'm repeating this over and over again because you got to practice this in your mind and it has to sink in. And that is the main hurdle with arrays that I've noticed with students. Oh, this prints 3. All right. Oh, now let's look at the test code. For this to run, we need to have an A. So let's define the array. We can define it like this. See, to define something, we provide a name for the thing, and we precede the name with the data type. So A is an integer, but oh, wait a minute. We're also going to follow the name with this open and close bracket. So that means it's an array of integers. And we can initialize it like this very conveniently. 3, 3, 11, and 7. This line right there creates the array A, initializes it to 3, 3, 11, and 7. And this is our comment up here. This is just for us to read. The compiler doesn't do anything with the comment other than ignore it. That's doing something with the comment. So now we can pass in now we can call the function. Now that we have A defined, we can pass it in here. So this is our test code. So we're going to define A, they're going to call total, and what should it print? It should print, well, I got to add them up, right? So let's see, that's 3 and 7 is 10, plus 11 is 21, plus 3 is 24. That's how I would add them up. So it prints 20. It should print 24. The function total doesn't print 24. The function total returns 24. And the return value that we get from calling the function is then passed into this output stream using the output operator right there. So the function doesn't print 24. The function evaluate, when we invoke the function with those two arguments, a and 4, the function returns 24, or it evaluates to 24. We say it like that. And that 24 becomes the right-hand side of an output operation. And that output operation operates on it sends the 24 into the output stream that's on the left-hand side, which is Cout, or the standard output stream, which by default is the console window right here. That's Cout. Cout is, see this window down there? That's Cout. By default, we can change it, by the way. We can change Cout using a redirection operator. Now Cout is the file name temp. It didn't print anything in the console window, but it created a file named temp. See, there it is, all temp, all pass, all test pass. So this is a redirection operator. It changes the assignment of standard output to a file. But by default, the standard output is the console, so that the printing happens here in the console. The Cout by default is the console, but can be reassigned to other output streams. So I'm going to delete this temp. I don't want that anymore, but I'm going to use the rm command. Remove temp. There we go. I don't want that output either. Remove output. There we go. Might as well delete this one too. What is going on there? I got some slowness. There we go. So now I was running an old version of the program. I wasn't running this one because, well, maybe this will compile actually. It shouldn't compile. It compiles. See that? When I run it, I think it's going to print 0 and all tests passed. But let's see. Let's see. It should print 0 and all tests passed. Or it just prints all tests passed. So this didn't print anything. Oh yeah, it wouldn't print 0 because that'd be a character 0. So this is actually what's happening here is this total is not declared as returning anything. So I think the compiler is doing that. I think it inserts a return 0. I think. So this statement, if that's true, what I'm saying, that statement would end up being this. And this, I think, does nothing. Apparently, I would guess that it's going to give us the same output. Let me test that. You know, I never did this experiment before. I'm just going to, oh, it does print a 0. Yeah, of course it prints a 0. I don't know what this returns. Maybe it returns a void. I don't get it. How does this work even?
You're writing the function total, right? Instead of predefined?
Oh, look at that now. Huh? Look at that crazy output there. Huh?
Are you writing the total function or is it predefined?
No, we're writing it here, see? If it's predefined, we can't declare it like this.
Okay, so doesn't there need to be something inside the brackets? Like, isn't it?
Yeah, I'm just doing nothing. I'm saying that the compiler is putting something in there. It's because there's no return statement. Because we're supposed to return an integer. See? And the compiler's not returning anything, so I'm doing experiments. and I'm getting actually into an advanced topic. I'm sorry about that. All right. So I think the compiler is inserting something in there, but it apparently is not inserting this in there. It's just, I don't know, maybe it's returning just a random number. That's what it looks like. It's returning something. Whatever happens to be sitting in memory just gets used. So some memory location is being used here. So it looks like it's returning a random value. But I want to talk a little bit more about this. That this compiles, and look at the number now. Look, it is changing all the time. That's a random number, isn't it? Look at that. Isn't that interesting? So what the thing is that if we compile this function and turn all warnings on, then it'll give us a warning because we didn't include a return statement in there. See that? No return statement in the function returning a non-void. Line 11. See, line 11 is right there. The compiler hit that point and said, hey, that's the end of the function, and you didn't have a return statement yet. So it generated this warning. It's not an error. It still generates the executable. But by default, and I don't know why they do this, they have those warnings turned off. I think it's no return. Yeah, that's a, that works too. No return statement. I don't remember, here I'm turning on all warnings. I'm turning on all warnings here, so minus W all. And if I just want to return on the warning for missing return statement, I don't know how to do it. Oh, here it is. Huh. So like it shows it to you right there in the error message. So we don't have to turn on all warnings. We can just turn on the warning that we're interested in, which is that the return statement is missing. But actually, it might be good to turn all warnings on because warnings are good. A warning doesn't stop the compiler from generating the executable, but it tells you it thinks something is wrong. So you can use this minus W, uppercase W, and ALL. So if we have a return in here, like return 0, this will eliminate that warning message. And this is called a stub. This function that we've implemented right here, it doesn't do what we want it to do. We just have a minimal implementation just to get it to compile. And the purpose of this is to check our test code. When we run this thing, it's going to print 0, right? So it shouldn't print 0. It should print 24. Let's get it to work now. So we have to read every value, 3, 3, 11, and 7, and we add them to some kind of accumulator. So we'll say int t for total. We start at 0. And then, for each value in A, do the following. T plus equals A of I. For each value in A, where I is a position in A. So maybe that's not very clear there. So this is just some pseudocode. We declare this I, set it to 0, and let I hit length and then exit the loop, but I hits length. Increment I at the bottom of the loop. Okay, there it is right there. There's our extra code. Don't forget we declared a t, which is like this total variable. And then we let I range across the values 0 to length minus 1. And for each of those values, we use it in this expression, a bracket I. And that pulls out the value at position I. So you want the value at position 0, the value at position 1, and so on. Those values are then added into t. I'm going to show you the alternative form of it. This t plus equals a is the same thing as writing this. You know, which one do you like? Do you like this one or this one? Which one do you like better? Style number 1 or style number 2? Which one is easier for you? They both do exactly the same thing. Which one do you like?
Probably 2.
2? Of course, that might appear on the exam, what I have right there, okay? I'm just going to comment it out. So you need to be used to this form. But in the beginning, maybe number 2 is easier. Well, let's make it easy to stare at the code. So we picked the form that was the easiest for us to read. So it should print 24 now. Oh, not yet. What's wrong? It's not going to print 24. It prints 4. How did it print 4? If I run it again, is it going to print 4 again? It does. Why is it printing 4? Well, look, if we compile it with the warnings turned on, it says, oh, look how useful the turning warnings on is. We forgot to put the return statement in here. After we calculate t, we need to return t. So we're missing the return statement. Look how useful that warning is. Maybe you're lost trying your coding and you can't figure out the bug. Just go ahead and turn the warnings on. Maybe that'll help. So now let's see if we fix the problem. See, I didn't save it. Look at that. All right. 24, we got it. Finally, we got it working. But the problem's not done yet because I want you to use assertions with automated test code. Here we're doing visual inspection. We expect to get a 24, run the program, and we verify that 24 was printed. But we can do that verification in code. So instead of printing this thing, we're going to compare the result to 24. This comparison right here. This is an expression. What I'm highlighting right there is an expression. We want that expression to be true. If the expression is false, that means the function, the total function, is not implemented correctly. So we want this expression to be true. We want total to return 24. So we use this function called assert to verify that for us. We assert that total A4 equals 24. If our assertion is wrong, terminate the program and let us know. And if the assertion is true, then what assert does is it does nothing. It just says, okay, you're asserting this and it's true and that's okay. Then we move on and then we print all tests passed. And that's what we're doing here. All tests passed. But what happens if we got the wrong, maybe that was an 8 there, right? We got the test code wrong. It should equal 25, but we mistakenly put 24 there. What's it going to do? Look at that. Assertion, total A4 equals 24 failed. That assertion failed. And it's in line 16 right there. So line 16 is failing. Now the error is either in our test code inside main, or the error is inside the function. And the error is in our test code. So we fix the test code, and we go through the process again of compiling and running. Now it says all tests pass, and we're 1 degree more confident that the program is correct. It doesn't prove it's correct, but it offers some level of confidence that it's correct. What if we made a mistake here? What if we, did something like this? Suppose we incremented t by 1, or by I. Maybe we did that. I think I may have seen that before. This is an incorrect implementation. So the assertion should fail. And it doesn't, because the thing is so slow right now that it's not working. There, the assertion has failed because we have an incorrect implementation. I'm going to show you something that I saw the other day in student code. He did this. He created a test vector that looked like this. See that? And he had this code in the loop up here. And he said that it passes. Oh, didn't pass. This should be, this is 0. Oh yeah, and then he said this was, the total is 6, right? That's what he said. The total, here, if this is the array, then the total should return 6. And it does. So he concluded he got the problem right. I said, wait a minute, this is not right, right? And said, oh, look at the test code. It's too regular looking. It's not good test code, see? So the thing about test code is the purpose of test code is not just to print all tests pass, because you can always get that done. It's to find the bug. So you've got to sort of challenge yourself or challenge your code. Let's declare another array B, and we're going to call this 1, 1. Well, let's put a negative number in there. So this total is 5. Maybe the first test passes now, but the second test fails. This should be B. Oh, look at this. Look at the warning. This is a warning. It compiled, but it said unused variable B, which is this particular warning. So we declared a B, we didn't use it, and then we got a warning. That was very useful because look at this. That's what I had. And if I didn't use that, if I didn't turn warnings on, it would have happily compiled. But with the warning on, it tells me that there's an unused variable B. Like, oh, we declared a B here, defined it, but we never used it. And it's like, normally you use something that you define. Otherwise, why define it? In fact, we have a bug here. We forgot to use B. The assertion failed. Look at this assertion. This assertion failed. The first assertion didn't fail because this particular test did not identify that bug. But the second assertion fails because this test was good enough to reveal that bug. So we go back to here, we do some investigation, fix this problem, try again. Now it works. What do you think? I gave you this is the template to do all the problems in this assignment, except for maybe I should show you the two-dimensional array. I should show you how to use a two-dimensional array. But this process of defining the function, implementing it, developing test code and using assertions, and printing all tests passed at the end. As we noticed today, turning on the warnings is useful. You might want to remember that. I think there's warnings here as well, aren't there? Let's see. No, the editor is not showing any problems with that. So let's work with two-dimensional arrays now. Let's write a function, the same function that sums up the values in an array that has 4 rows and 3 columns. I want to try something here. How can I comment those out? Yeah, toggle comment. So I'm on a Mac, so this is command slash. Didn't work. Command slash. Look at that. Isn't that nice? That's easier than that's a bunch of single line comments. Rather than the multi-line comment looks like this. It takes longer to type. You know, that's the multi-line comment. And then to take it out, you got to delete here, you got to delete here. But a single line comment is nice because the editor lets us just do command slash to turn it on and off. So here we have the function. We want to find the total. We have now a two-dimensional array. Let's look at an example. And you know, this is what A will equal. A equals this. 3 minus 1, 0. 4, 11, 1. 7, 20, 0. 0, 2, 5. There is a two-dimensional array. It has 4 rows and 3 columns. That's A. That's our example. And so we need to create that array. Let's do that. That's we're going to create this test code here. So the array looks like this. The array definition. We list out the rows first. So it's 3, -1, 0, 4, 11, 1, 7, 20, 0, 0, 2, 5. Oh, we got to do the total here. And the function only takes one argument because we're specifying the size of the array right there. What's the total of this? That's 7. That gives us 14. That's 34, 35, 46, 50, 53, 52. 52 cards. We'll get rid of this one. Oh no, we'll have another test. Let's do this test. If I put a 0, it sets the entire array to zeros. But I need to give a size there. Here, the size is implied by this list. Here, the size could be implied by this. If I left these out, it would make a 1-by-1 array, I think. But we want to have the array to be 4 rows, 3 columns, but we want everything set to 0, so this syntax will work. And this total, by the way, is 0. So we have some test code. Now we need to implement the function. Well, before we implement the function, let's test the test code. Let's put in a stub. We'll return 0. So this test should work. Let's go ahead and verify that. This test of B, this should pass because we're just returning a 0 in our stub. The stub is an incomplete function just for the purposes of getting the program to compile and to start testing. So this is going to return 0, so this is going to pass. We need this extra test case here to catch the error. So we should have a failure in line 27. Uh-oh. So error, declaration of A is multidimensional, must have bounds in all dimensions except the first. And we got to do this. But I don't want to talk about the reason why, so I'm going to do that. So that worked. Now let's run it. And line 27, as we predicted, there's an assertion failure. Line 27 right there. So that's failed. But we passed this one because this test code is not good enough to catch that. All right, so let's go ahead and do, now that we're confident that we got some test code written up and it runs, it compiles, it runs, let's go ahead and try to implement the function. So we have this accumulator variable t to store the total. Now we got to run across the number. What we're going to do is range across the rows. So I'm going to use R here. So R goes from 0 to 4, but it quits the loop at 4. So we're gonna let R range across the rows. And then we're going to let C range across the columns. There's only 3 columns, so we stop there. There's a danger in copying code because I could have used the old variable. See, do you see how I'm checking my indentation? This outer for loop is closed in line 19, and that brace, line 19, is right underneath the F, which is the beginning of the for statement. So that's an important visual cue to show you the extent of the for loop. Inside the for loop, there's only one statement. Well, it's another for loop. And that statement is a substatement, so it's indented relative to its parent. This is very important. This inner for loop has also one substatement, which is also indented relative to its parent. That indentation is very important. Now, A is 2-dimensional. And that's the reason we've got 2 indices, R and C, one for rows, the other for columns. So we use this syntax here. A bracket R bracket C, like that. We use that syntax to access the value at row position R and column position C. So if R were 1 and C were 2, let's see, R were 1, this is row 1, this is row 0, by the way. So this is row 1, and column 2, well, this would be column 1, column 0 rather, column 1 and column 2. So that means A of 1, 2 equals 1. It's this one right there. That's A of 1, 2. You see that? Row 1, column 2. Starting the count from 0. Computers start counting from 0. In the distant future, everyone will know how to program. And then everyone suddenly, naturally starts counting from 0. So we say, well, how many things are over there? And they'll go, oh, let's see, 0, 1, 2, 3. Oh, there's 4 things over there. So, I'm just joking. But computers start counting from 0. And I don't know if humans will ever start counting from 0 or not. But if you're a programmer, you got to learn how to count from 0. All right. So we've got the function implemented. I'm going to save the file. And now we're going to run it. It should say all tests pass because I'll have a complete implementation here. So we need to compile. It works. Run. All tests pass. We got it. Now, we don't know absolutely for sure that we got it we got it correctly done, because maybe the test code is inadequate. But we did the best we could. You know, I created a test that I know tested a boundary case that would not catch the bug. I deliberately inserted a bug that this boundary test wouldn't catch, because I'm trying to make the test code robust. It's important to do what are called the boundary cases. You know, an array of all zeros, that's a special case, right? This array here is not a special case. And I even threw in a negative number just to make sure it wasn't special, because if everything was positive, that would be a special case, wouldn't it? But throw a negative number in there, it's the test case is a little bit more generic. All right, so that's that. Are we done? I think that's enough. There's two examples to illustrate arrays and also to illustrate this process of writing test code with assertions.